In algebra and geometry, a group action is a description of symmetries of objects using groups. The essential elements of the object are described by a set, and the symmetries of the object are described by the symmetry group of this set, which consists of bijective transformations of the set. In this case, the group is also called a permutation group or transformation group. A group action is an extension to the definition of a symmetry group in which every element of the group acts like a bijective transformation of some set, without being identified with that transformation. This allows for a more comprehensive description of the symmetries of an object, such as a polyhedron, by allowing the same group to act on several different sets of features, such as the set of vertices, the set of edges and the set of faces of the polyhedron. If G is a group and X is a set, then a group action may be defined as a group homomorphism H from G to the symmetric group on X. The action assigns a permutation of X to each element of the group in such a way that the permutation of X assigned to the identity element of G is the identity transformation of X. A product GH of two elements of G is the composition of the permutations assigned to G in H. Since each element of G is represented as a permutation, a group action is also known as a permutation representation. The abstraction provided by group actions is a powerful one, because it allows geometrical ideas to be applied to more abstract objects. Many objects in mathematics have natural group actions defined on them. In particular, groups can act on other groups, or even on themselves. Despite this generality, the theory of group actions contains wide-reaching theorems, such as the orbit stabilizer theorem, which can be used to prove deep results in several fields. Definition: if G is a group and X is a set, then a group action I of G on X is a function that satisfies the following two axioms as Gx, compatibility, Gh, X equals G. Hx, for all G, H in G and all X in X, identity, Ex equals X for all X in X. The set X is called a G-set. The group G is said to act on X. From these two axioms, it follows that for every G in G, the function which maps X in X to Gx is a bijective map from X to X. Therefore, one may alternatively define a group action of G on X as a group homomorphism from G into the symmetric group Sim, X, of all bijections from X to X. In complete analogy, one can define a right group action of G on X as an operation XA, Gx mapping to Xg in satisfying the two axioms, compatibility, X. Gh, equals H for all G, H in G and all X in X. Identity, Xe equals X for all X in X. The difference between left and right actions is in the order in which a product like Gh acts on X. For a left action H acts first and is followed by G, while for a right action G acts first and is followed by H. Because of the formula 1 equals Ha1 Ga1, one can construct a left action from a right action by composing with the inverse operation of the group. Also, a right action of a group G on X is the same thing as a left action of its opposite group G on X. It is thus sufficient to only consider left actions without any loss of generality. Examples: the trivial action of any group G on any set X is defined by Gx equals X for all G in G and all X in X. That is, every group element induces the identity permutation on X. In every group G, left multiplication is an action of G on G, Gx equals Gx for all G, X in G. In every group G, conjugation is an action of G on G, Gx equals Gx Ga1. An exponential notation is commonly used for the right action variant, Xg equals Ga1 Xg. It satisfies H equals Xgh. The symmetric group Sn and its subgroups act on the set 1, n by permuting its elements. The symmetry group of a polyhedron acts on the set of vertices of that polyhedron. It also acts on the set of faces or the set of edges of the polyhedron. The symmetry group of any geometrical object acts on the set of points of that object. The automorphism group of a vector space acts on the vector space. The general linear group GL, N, K, and its subgroups, particularly its Lie subgroups, orthogonal group O, N, K, special orthogonal group SO, N, K, and symplectic group SP, N, K are Lie groups that act on the vector space Kn. The group operations are given by multiplying the matrices from the groups with the vectors from Kn. The projective linear group PGL, n plus 1, K, and its subgroups, particularly its Lie subgroups, which are Lie groups that act on the projective space Pn, K. This is equivalent of the action of the general linear group on projective space. Particularly notable is PGL, 2, K, the symmetries of the projective line, which is sharply 3-transitive, preserving the cross ratio. The Ma paragraph bias group PGL, 2, C, is of particular interest. The isometries of the plane act on the set of 2D images and patterns, such as wallpaper patterns. The definition can be made more precise by specifying what is meant by image or pattern. For example, a function of position with values in a set of colors. The sets acted on by a group G comprise the category of G-sets in which the objects are G-sets and the morphisms are G-set homomorphisms, functions phi x or y such that x equals f, gx, for every G and G. The Galois group of a field extension Lk acts on the field L but has only a trivial action on elements of the subfield K. Subgroups of Gal, Lk, correspond to subfields of L that contain K, that is intermediate field extensions between L and K. The additive group of the real numbers acts on the phase space of well-behaved systems in classical mechanics by time translation. If T is in A and X is in the phase space, then X describes a state of the system, and T plus X is defined to be the state of the system T seconds later if T is positive or AT seconds ago if T is negative. The additive group of the real numbers acts on the set of real functions of a real variable in various ways, with x equal to for example f, x plus t, f, x, plus t, f, z, f, x, a, f, x plus t, a, or f, z, plus t, but not f, z plus t. Given a group action of G on X, we can define an induced action of G on the power set of X, by setting G U equals G where U are U for every subset U of X and every G in G. This is useful, for instance, in studying the action of the large Mathieu group on a 24 set and in studying symmetry in certain models of finite geometries. The quaternions with norm 1, as a multiplicative group, act on M3. For any such quaternion, the mapping f, x, equals zx za, is a counterclockwise rotation through an angle I plus or minus about an axis v. Z is the same rotation. See quaternions and spatial rotation. Types of actions. The action of G on X is called transitive if X is non-empty and if for any X, Y and X there exists a G and G such that Gx equals Y. Faithful if for any two distinct G, H and G there exists an X in X such that Gx are permel Hx. Or equivalently, if for any Ga permel E in G there exists an X in X such that Gx are permel X. Intuitively, in a faithful group action, different elements of G induce different permutations of X, free if, given G, H and G, the existence of an X in X with Gx equals Hx implies G equals H. Equivalently, if G is a group element and there exists an X in X with Gx equals X, then G is the identity. Regular if it is both transitive and free. This is equivalent to saying that for any two X, Y and X there exists precisely one G and G such that Gx equals Y. In this case, X is known as a principal homogeneous space for G or as a G-torsor. N-transitive if X has at least n elements and for any pairwise distinct x1, a euro, xn and pairwise distinct y1, a euro, and there is a G and G such that Ga xk equals ik for 1 a permel currency K a permel currency n. A two-transitive action is also called doubly transitive, a three-transitive action is also called triply transitive, and so on. Such actions define two transitive groups, three transitive groups, and multiply transitive groups. Sharply n-transitive if there is exactly one such G. Primitive if it is transitive and preserves no non-trivial partition of X. See primitive permutation group for details. Locally free if G is a topological group, and there is a neighborhood U of E in G such that the restriction of the action to U is free. That is, if Gx equals X for some X and some G in U, then G equals E. Irreducible. If X is a non-zero module over a ring R, the action of G is a linear, and there is no non-zero proper invariant submodule. Every free action on a non-empty set is faithful. A group G acts faithfully on X if and only if the corresponding homomorphism G sim, X, has a trivial kernel. Thus, for a faithful action, G embeds into a permutation group on X. Specifically, G is isomorphic to its image in sim, X. The action of any group G on itself by left multiplication is regular, and thus faithful as well. Every group can, therefore, be embedded in the symmetric group on its own elements, sim, G. This result is known as Cayley's theorem. If G does not act faithfully on X, one can easily modify the group to obtain a faithful action. If we define n equals G and gar Gx equals X for all X in X, then n is a normal subgroup of G. Indeed, it is the kernel of the homomorphism G sim, X. The factor group Gn acts faithfully on X by setting X equals Gx. The original action of G on X is faithful if and only if n equals E. Orbits and stabilizers. Consider a group G acting on a set X. The orbit of a point X in X is the set of elements of X to which X can be moved by the elements of G. The orbit of X is denoted by Gx. The defining properties of a group guarantee that the set of orbits of X under the action of G form a partition of X. The associated equivalence relation is defined by saying X to Y if and only if there exists a G and G with Gx equals Y. The orbits are then the equivalence classes under this relation. Two elements X and Y are equivalent if and only if their orbits are the same. That is, Gx equals Gy. The group action is transitive if and only if it has only one orbit, that is if there exists X in X with Gx equals X. This is the case if and only if Gx equals X for all X in X. The set of all orbits of X under the action of G is written as Xg, and is called the quotient of the action. In geometric situations it may be called the orbit space, while in algebraic situations it may be called the space of coinvariants, and written Xg. By contrast with the invariants, denoted Xg, the coinvariants are a quotient while the invariants are a subset. The coinvariant terminology and notation are used particularly in group cohomology and group homology, which use the same superscript-subscript convention. Invariant subsets: if Y is a subset of X, we write Gy for the set G are Y a Y and G a G. We call the subset Y invariant under G if Gy equals Y. In that case, G also operates on Y by restricting the action to Y. The subset Y is called fixed under G if Gy equals Y for all G and all Y and Y. Every subset that is fixed under G is also invariant under G, but not vice versa. Every orbit is an invariant subset of X on which G acts transitively. The action of G on X is transitive if and only if all elements are equivalent, meaning that there is only one orbit. A G-invariant element of X is X and X such that Gx equals X for all G a G. The set of all such X is denoted Xg and called the G-invariance of X. When X is a G module, Xg is the zeroth group cohomology group of G with coefficients in X, and the higher cohomology groups are the derived functors of the functor of G-invariance. Fixed points and stabilizer subgroups: given G and X with Gx equals X, we say X is a fixed point of G and G fixes X. For every X in X, we define the stabilizer subgroup of X as the set of all elements in G that fix X. This is a subgroup of G, though typically not a normal one. The action of G on X is free if and only if all stabilizers are trivial. The kernel N of the homomorphism G sim, X, is given by the intersection of the stabilizers Gx for all X in X. If N is trivial, the action is said to be faithful. Let X and Y be two elements in X, and let G be a group element such that Y equals Gx. Then the two stabilizer groups Gx and Gray are related by Gray equals Gx gar1. Proof: by definition, H are Gy if and only if H. Gx equals gx. Applying Gar1 to both sides of this equality yields x equals x equals x. That is, Gar1 hectogramma gx. The above says that the stabilizers of elements in the same orbit are conjugate to each other. Thus, to each orbit, one can associate a conjugacy class of a subgroup of G. Let denote the conjugacy class of H. Then one says that the orbit O has type if the stabilizer of some any x in O belongs to. Orbit stabilizer theorem and Burnside's lemma, orbits and stabilizers are closely related. For a fixed x in X, consider the map from G to X given by GA-Gx for all G a G. The image of this map is the orbit of X and the co-image is the set of all left cosets of Gx. The standard quotient theorem of set theory then gives a natural bijection between Gx and Gx. Specifically, the bijection is given by Hgx. This result is known as the orbit stabilizer theorem. From a more categorical perspective, the orbit stabilizer theorem comes from the fact that every G set is a sum of quotients of the G set G. If G and X are finite, then the orbit stabilizer theorem, together with Lagrange's theorem, gives. This result is especially useful since it can be employed for counting arguments. A result closely related to the orbit stabilizer theorem is Burnside's lemma, where Xg is the set of points fixed by G. This result is mainly of use when G and X are finite, when it can be interpreted as follows: the number of orbits is equal to the average number of points fixed per group element. Fixing a group G, the set of formal differences of finite G sets forms a ring called the Burnside ring of G, where addition corresponds to disjoint union, and multiplication to Cartesian product. Group actions and groupoids. The notion of group action can be put in a broader context by using the action groupoid associated to the group action, thus allowing techniques from groupoid theory such as presentations and fibrations. Further, the stabilizers of the action are the vertex groups, and the orbits of the action are the components of the action groupoid. For more details, see the book Topology and Groupoids referenced below. This action groupoid comes with a morphism which is a covering morphism of groupoids. This allows a relation between such morphisms and covering maps in topology. Morphisms and isomorphisms between G-sets. If X and Y are two G-sets, we define a morphism from X to Y to be a function phi X or Y such that f, Gx, equals Gf, X. For all G and all X in X, morphisms of G-sets are also called equivariant maps or G-maps. The composition of two morphisms is again a morphism. If a morphism F is bijective, then its inverse is also a morphism, and we call F an isomorphism, and the two G-sets X and Y are called isomorphic. For all practical purposes, they are indistinguishable in this case. Some example isomorphisms: every regular G action is isomorphic to the action of G on G given by left multiplication. Every free G action is isomorphic to G A, S, where S is some set and G acts on G A, S by left multiplication on the first coordinate. Every transitive G action is isomorphic to left multiplication by G on the set of left cosets of some subgroup H of G. With this notion of morphism, the collection of all G sets forms a category. This category is a Grothendieck topo. Continuous group actions. One often considers continuous group actions. The group G is a topological group, X is a topological space, and the map G A, X A X is continuous with respect to the product topology of G A, X. The space X is also called a G-space in this case. This is indeed a generalization, since every group can be considered a topological group by using the discrete topology. All the concepts introduced above still work in this context, however we define morphisms between G-spaces to be continuous maps compatible with the action of G. The quotient Xg inherits the quotient topology from X, and is called the quotient space of the action. The above statements about isomorphisms for regular, free and transitive actions are no longer valid for continuous group actions. If G is a discrete group acting on a topological space X, the action is properly discontinuous if for any point X in X there is an open neighborhood U of X in X, such that the set of all G and G for which consists of the identity only. If X is a regular covering space of another topological space Y, then the action of the deck transformation group on X is properly discontinuous as well as being free. Every free, properly discontinuous action of a group G on a path-connected topological space X arises in this manner. The quotient map X(G) is a regular covering map, and the deck transformation group is the given action of G on X. Furthermore, if X is simply connected, the fundamental group of Xg will be isomorphic to G. These results have been generalized in the book Topology and Groupoids referenced below to obtain the fundamental groupoid of the orbit space of a discontinuous action of a discrete group on a Hausdorff space, as, under reasonable local conditions, the orbit groupoid of the fundamental groupoid of the space. This allows calculations such as the fundamental group of the symmetric square of a space X, namely the orbit space of the product of X with itself under the twist action of the cyclic group of order 2 sending to. An action of a group G on a locally compact space X is cocompact if there exists a compact subset A of X such that GA equals X. For a properly discontinuous action, cocompactness is equivalent to compactness of the quotient space Xg. The action of G on X is said to be proper if the mapping G A, X that sends A is a proper map. Strongly continuous group action and smooth points. A group action of a topological group G on a topological space X is said to be strongly continuous if for all X in X, the map GA-GX is continuous with respect to the respective topologies. Such an action induces an action on the space of continuous functions on X by defining X equals F, Gar1X, for every G and G, F a continuous function on X, and X and X. Note that, while every continuous group action is strongly continuous, the converse is not in general true. The subspace of smooth points for the action is the subspace of X of points X such that GA-GX is smooth. That is, it is continuous and all derivatives are continuous. Variants and generalizations. One can also consider actions of monoids on sets, by using the same two axioms as above. This does not define bijective maps and equivalence relations however. See semigroup action. Instead of actions on sets, one can define actions of groups and monoids on objects of an arbitrary category, start with an object X of some category, and then define an action on X as a monoid homomorphism into the monoid of endomorphisms of X. If X has an underlying set, then all definitions and facts stated above can be carried over. For example, if we take the category of vector spaces, we obtain group representations in this fashion. One can view a group G as a category with a single object in which every morphism is invertible. A group action is then nothing but a functor from G to the category of sets, and a group representation is a functor from G to the category of vector spaces. A morphism between G sets is then a natural transformation between the group action functors. In analogy, an action of a groupoid is a functor from the groupoid to the category of sets or to some other category. In addition to continuous actions of topological groups on topological spaces, one also often considers smooth actions of Lie groups on smooth manifolds, regular actions of algebraic groups on algebraic varieties, and actions of group schemes on schemes. All of these are examples of group objects acting on objects of their respective category. See also, gain graph, group with operators, monoid action, Lie group action, notes. References: Ashbacher, Michael. Finite Group Theory. Cambridge University Press. ISBN A978-0-521-78675-1. MRA 1777008. Brown, Ronald. Topology and Groupoids, Booksurge plc, ISBN 1-4196-2722-8. Categories and Groupoids, P. J. Higgins, downloadable reprint of Van Nostrand Notes in Mathematics, 1971, which deal with applications of groupoids in group theory and topology. Dummett, David. Richard Foote. Abstract Algebra ed. Wiley. ISBN A0-471-43334-9. I. Minking. Chang, Shotty E. A Course on Abstract Algebra. World Scientific. ISBN A978-981-4271-88-2. Rotman, Joseph. An Introduction to the Theory of Groups. Graduate Texts in Mathematics 148 ed. Springer Verlag. ISBN A0-387-94285-8. Smith, Jonathan D. H. Introduction to Abstract Algebra. Textbooks in Mathematics. CRC Press. ISBN A978-1-4200, 6371-4. External links. Haswinkel, Mikhail, ed., Action of a Group on a Manifold, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Weierstein, Eric W., Group Action, MathWorld.